Hi, today I'll be talking about estimating regression parameters. To estimate regression, one would use two variables, x and y, in a linear relationship and have data points in a scatter plot to determine true regression line with a coefficient of determination. One of the main topics to talk about is simple linear regression model. This is a model that basically puts a best of fit line in data based in a scatter plot and finds a formula which is the least squares regression line, or LSRL. And three ways to describe the scatter plot would be form, direction, and strength. For the scatter plot, correlation is very important. It measures the direction and strength of the linear relationship between the two quantitative values. So based on the graph on the right, I could predict on average for each additional dollar increase, the predicted number of meets increases by 0.735. The LSRL is basically the correlation between the data points and the line. Take the first graph. You would find the distance between each point and the LSRL and put that on a graph. That is the residual plot, and it is used to explain how good a model is. Having no pattern is really good. If I would take all the points from the residual plot and place them on a bell curve, it would show a normal distribution. Residuals are basically the distance between the point and the true regression line, or observed minus predicted. The line is what you're trying to predict, and the scatter plot points are the observed. Influential and outlier points can affect your LSRL. They are extreme values in one direction that can pull or greatly affect the slope and would mess up your estimations. So R squared is the coefficient of determination, and it's basically the percent of variation. And some of the key players are the 3 points below. So breaking down the coefficient of determination, SST, which is the one in red, is the worst possible error data can have. And SSE and SSP, SSE is in gray, SSP is in green, are some of the values that are used to computate R squared. Applying this into computer engineering, let's say that there's data on microprocessors and the company is trying to figure out whether or not spending more money for better products is correlated to the microprocessor's ability to increase or decrease. So one can use an LSRL model and determine whether or not the increase of money spent on products correlates to the performance. So let's say y is equal to 1.26 plus 0.1 is the formula founded, and one could predict that on average for each additional dollar spent, the predicted increase of performance by the microprocessor increases by 0.1%.